So we're going to go through something called Kirkhoff's laws, which are basically like a set of rules that we apply when trying to figure out like exactly the question you asked, like how much current, like how much, what like all of the current at the different parts of the circuit. Like if we have a more complicated circuit than the ones that we've been dealing with. Okay, so we have to talk about something called a junction. So let me draw for you what a junction is. So let's say that you have, so a junction is basically whenever you have 3 or more wires coming together. Okay, so like let's say that we have this comes in. Well, I guess it could just be two or more. Sorry, 2 or more wires coming together. So let's say that we've got that's like the simplest junction that I can think of, right? So let's say that this is like I1 and this is I2. This is the junction where they come together. Okay, and then that's I3 leaving the junction. Okay, and so the thing about a junction is you can't have any charge building up there. Okay, think of it as like the charge, and also the charge has to be conserved. So like so 2 special things about a junction: no charge buildup. Okay, and like as always, charge is conserved. So there's something called the junction rule. Which is just that the sum of the currents coming in have to equal the sum of the currents going out. Okay, so if we look at our little mock example over here, it would be like I1 plus I2 equals I3. Right, so all of the current coming into the junction has to equal all of the current going out of the junction. Okay, so as current flows around a loop, we've already said this a couple of slides ago. As current goes around the loop, the change in potential energy has to equal 0. Remember we said that back here when we were talking about this. We were talking about this diagram here, and we were saying like there's a potential like increase across the battery, and then it's an equipotential line, and then there's a potential drop across the resistor, and those two, like the plus the minus, equals 0, right? So all the way, if you draw a loop all the way around the circuit, it has to equal 0. Okay, so that's actually a rule. Okay, it's called the loop rule. So let me just draw a little example to explain what I mean. So let's say you have this point in a circuit, and I'm going to call that V1, and I have this point, and I'm going to call that V2, and I have this point here, and I'm going to call that V3. Okay, and from here to here is just V2 minus V1. From here to here is just V3 minus V2. And from here to here is just V1 minus V3. Okay? Now let's put numbers in just for fun. Let's say that this is 0 volts, like V1 is 0 volts. This is 5 volts. And let's say this is 9 volts. Okay? The loop rule says that if I go all the way around the loop, the sum of the change in voltages has to equal 0. So let's just see if that's true. So if I go from V1 to V2, so V2 minus V1, that's 5 volts, right? 5 volts minus 0 is 5 volts, okay? And then if I go from V2 to V3, the change in potential there is just V3 minus V2. right? So that's 9 minus 5, which is 4 volts. And then if I go from V3 back to V1, that's V3 minus V1, that's 0 minus 9 volts, which is minus 9 volts. If I add these three things together, I get 0 volts. Right? So if I come back to the beginning place, the change in potential is 0. Does that make sense? Yeah? Okay. So this is called the loop rule. Okay, the loop rule just says that the sum of the change in potentials has to equal 0. Okay. So in applying the loop rule, you have to be really careful with signs. The only way to screw this up is if you make a mistake with the signs. And this bottom part of the page describes to you what the conventions are. So, and again, these are just arbitrary conventions that we've all decided to use. So this direction, as I go from left to right, is like, so I decide which direction the loop is going to go, and you'll see an example in a second. Like, I literally draw like a picture of a loop in my circuit. And so if you're going from, like, if you're going through the battery, so there's three like things. The first is the battery. Okay, so the battery. So if you go through the battery from the negative terminal of the battery to the positive terminal of the battery, then we say that that's an increase in potential. So these things in yellow are the change in potential. Right? So if I go from a negative terminal to the positive terminal, if like the direction of my loop goes in that direction, then that corresponds to a positive increase in potential. Okay? If I go in the opposite direction, then that corresponds to a negative change in potential. Okay? And again, this is just like an arbitrary convention. Okay? So that's the thing with the battery. The second one is the thing with the resistors. So if the direction of the loop is in the same direction as the current, then that corresponds to a negative drop in potential. And like, who cares why? It's just what we've decided. It's just what we've agreed on. Okay, so like if the direction of my loop goes in the same direction as my current, then it's actually a negative change in potential. If the direction of my loop goes in the opposite direction of the current, then it's a positive change in potential. Okay, so that's the second one. The third one is to do with capacitors. So that's the little picture down here, capacitors. And capacitors follows the same convention as resistors. So if the direction of your loop goes in the same direction as the current, then the change in potential, remember the change in potential for a capacitor is just Q over V, right? So if the loop direction is in the same direction as the current, then it's a negative change in potential. If the loop direction is in the opposite direction of the current, then the change in potential is positive. Okay, these are just rules. Okay, so let's apply this. And here, this is like strategy for how to solve, like the ultimate goal is like kind of an answer to your question. How do we figure out how much current is going through each resistor? That's our ultimate goal. So we're going to apply these like 4 rules to be able to figure that out. Right? Because it's not immediately obvious if you look at a circuit like this, and if the resistances are not the same, how do we know how much current is going through one versus the other? Okay? So the first thing that we do, and I'm going to break, I promise, in just 2 minutes. The first thing that we do is we label, I mean, the rules are outlined up here. We label the currents with directions. Okay, so I would like start with the battery. You know, this is the positive, this is the negative. So you know the current is going through here. It's going to go down like this, right? It's going to split here. Some of it's going to go there, some of it's going to go there, right? So we might want to have like a different like label for this. Like we could call this I1, right? That's going to be I1. That's the same current all the way through. And then let's call this like I2 and I3 over here. So this current here is I2. This current here is I3. Okay, and then it comes back together, and so this is I1 again. And then I1. Okay, so step one done, right? We've labeled so step one, we've labeled the current, so check. Okay, so I'll just write it here so you can, so label current. Okay, so step two is to apply the junction rule. Okay, so like what's the junction rule? The junction rule is just whenever you have current going in, it has to equal the current going out. How many junctions are there? There's two. There's one at A, there's one at B. Okay, so what junction rule would you write for A? Okay, so junction. So you would say I1 equals I2 plus I3. That's at junction A. And then what would you say at junction B? I2 plus I3 equals I1. Okay, so those are clearly redundant, right? So I really don't need both. They're the same equation. That won't always be the case though, right? So like if you have a more complicated situation, you might have like multiple junction rules where the equations are actually like sort of numerically different. Okay, so step three is define the loops with directions. Okay, so define loops. Okay, so this is the tricky part. So let's use different colors. How many different loops do you think? Like, and a loop is kind of just a path. Like think of like an individual electron or like charged particle moving through this. Like how many different ways could it move through? Yes, that's true. But there's actually 3 loops, right? There's this middle loop here. And I mean, you can define just a loop as like coming back to the same place, right? Starting and then coming back to the same place. You're absolutely right. There's only like really 2 like paths, but there's 3 loops, right? So this is a loop here, and I'm just going to draw it like this. Right? So I can start, like go all the way around here and then come back to the same spot. Okay, so I'm going to call that loop 1. Okay, and then the other 2 loops are the ones that like I think are more obvious that you probably saw. So let me do it in a different color. So let me call loop 2 this one here. So starting here, oh, I should use maybe a red. Okay, so starting here, going kind of like all the way around, right? I'm going to call that loop 2. And then loop 3 would be like starting here and like going back like this. Okay, so that's loop 3. Okay, so let's take a break. What you might want to try during the break is writing, like, so doing the 4th step. And the 4th step is to basically apply these 3 rules to write out equations for each of the 3 loops. Okay, maybe we could do one together. Let's do one together just so you can see what I mean, and then you can try 2 and 3 on your own. Okay, so loop. Let me go back to this color.
Like if the current on R2 is going down and the current on R1 is going down towards I1, how can an electron go the
it's like, it's just, it depends on the resistances, first of all. Like we don't know, like it would depend on their comparative resistances. We're just defining like loops as like, I'm coming back to the same starting point. Okay, don't worry so much about, we're gonna take care of that with we're gonna address your question with the fourth step. Okay, just hold on and I think you'll see what I mean. It's a good question. Okay, let's just write out the loop rule for the middle loop. Okay, so here I'm going through, so here the direction of my loop over here is in the same direction as the current or the opposite direction of the current? Same direction, right? So this is going to be, so loop 1 is going to be current 2 times R2, but it's going to be negative, right? Based on this definition up here, right? Remember, if the loop goes in the same, like here's my loop, it's pointing down, my current is pointing down, so it has to be negative, right? So loop 1, the first term is negative I2 times R2, right? What does that equal? What is that quantity? What's I times R? Voltage, right? So it's going to have a voltage drop of like I times R, right? And then what about this one? So the direction of the current is down, but the direction of the loop is up, right? Do you see that? My green arrow is down, my pink arrow is up. So it's going to be plus I1 times R1, and that's going to equal 0. So that's my equation for the first loop. Yeah?
Just to clarify, so is it actually, should the sum for I should be negative I3 as we labeled it, R2 plus I2, R1 based on the
Oh yeah, that's a good point. Yeah, thanks for catching that. We called that I3. Yes. So yeah, that's a good catch. Yeah, that should be I3. Yeah, because that current is actually I3 going through there. And then there should be I2. Yeah, nice. Yeah, so it's the current that's actually going through the resistor that you care about. Okay, thank you. Was that your question too? Yeah, okay. So let's take a break and try the other two loops, like using that logic. And let's come back at 5 past, so 15 minutes, 5 past 8. Okay, so let's pick up again. Okay, so loop 2, let's do loop 2 now. So using the same kind of rules that we did for loop 1, so let's say I start here on the loop. Okay, and I'm going in the same direction. I'm going from negative to positive in the battery, right? Like as I go around this red loop. So that's going to be a plus, like whatever the voltage of the battery is, right? And then I go around here. Happily, I don't meet any other components until over here, right? And so the current is going in the same direction as the loop, right? Here's my loop. Right, so it's going to be minus I3 times R2, right? Because that's just how we labeled it, right? I kind of regret that now, like labeling it that way, but that's what we did, right? And that's going to equal 0, okay? So from there, I could actually calculate what I3 is, right? I3 is just going to be the voltage of the battery divided by R2, right? Okay, so now let's do the last loop, loop 3. So loop 3, okay, so let's again let me start down here, okay? So I'm going in this direction. I'm going from negative to positive. So I'm going like, in that direction in the loop. So that's going to be again plus like the voltage of the battery, right? And then I'm coming around here. I hit this component, this R1, right? So this is going to be minus R2, or sorry, I2 times R1, right, equals 0. Okay, and so similarly, I could calculate what I2 is. I2 is just going to be E divided by R1. Okay, and so that's really great. It allows me to calculate the current through each of those two components. Let me just show you something to kind of like bring it all together. Okay, I know from my loop rule, remember I wrote out these kind of redundant loop rules. Right? I know from my loop rule that I1 equals I2 plus I3. Okay? Now I know what I2 and I3 are, right? So I could substitute those two things in. So I know that that equals E over, so I2, let's see, was E over R1 plus E, where that's just the voltage of the battery, over R2, right? So I1, I could pull the voltage of the battery out, 1 over R1 plus 1 over R2, right? And I know that this is just equal to V, right? So what is this beginning to look like? Adding resistance in parallel, right? All I have to do is manipulate. I'm gonna like manipulate this equation a little bit, right? I'm gonna rearrange these. You see, rearrange these so that E, which is just V, equals the current times 1 over R1 plus 1 over R2 to the negative 1. Right, because I flipped it, right, so that I could solve. I just rearranged this equation here, and I solved for voltage, right? And all this just to show you that this is Ohm's law, right? This is V equals IR, and this is the REQ for resistors in parallel. Right, so for parallel resistors. So that should be like a reassuring thing for you. The fact that like when we apply our loop rule and we substitute in our two currents that we calculated, or sorry, when we apply our junction rule, right, our I1 equals I2 plus I3, we substitute in the two with the two currents that we calculated from our loop rule, then we get out of that Ohm's law such that R is the equivalent resistance for adding resistors in parallel, which is what this is. This is two resistors in parallel. Okay, so that should be like reassuring to you. So if R1 is bigger than R2, which resistor dissipates more power? Did any of you do that over the break? R1 or R2? Which one dissipates more power? How many people think R1? How many people think R2? Okay, yeah, so it's R2, right? We know that power equals I times delta R, right? R2 dissipates more power because it has more current, right? And it's the same, remember, same delta V. Right? So if this is the same for both resistors, and we have more current going through R2, then that has to dissipate more power. Yeah?
Can you explain how we know that there's more current going through R2 rather than R?
How do we know that there's more current going through?
From the equations, like the loop equation, so it's the same. Sorry, I didn't hear.
That's a good question. So,
Like we know v is constant, but like since everything's in variables, how would you know that?
yeah. So R1, R2. Yeah, sorry, that's only true if we're using that. I mean, they tell us that. We don't know that. You're absolutely right. We don't know it like from what we just worked out. But it's in the question. So we're starting with the assumption that R1 is bigger than R2, just like let's say. If that's the case, so the bigger the resistance, the smaller the current. Like think of it like, let's say R2 is, so we're saying R1 is bigger. So this is, let's just say that this is bigger. Okay, when the current gets to this point, less of it's going to go down this branch, okay, because the resistance is bigger. Okay, so if R2 is smaller, then more current will go through it. So more current, because the voltage is the same, constitutes more power. Okay, so but it, like again, we wouldn't have known that from the circuit itself, like from all of what we worked out. It was just because the question said it, like we were told it, but that's, yeah.